And welcome to this webinar on Energy Technology Perspectives 2014. I am Marcus Bråke. I'm actually doing this from Stockholm in Sweden. The rest of the team from the IEA is in Paris. We have about 500 registered participants at this webinar, which is a pleasure, of course, to see such great interest in this topic. I will soon be passing the word to Jean-François Gagnier, who's head of the ETP division at the IEA, but first just a few housekeeping issues. I will be moderating this webinar. We will be doing this for about 2 hours. You will hear from a number of the lead authors of ETP. Since we're so many people, we've actually muted all your microphones, so unfortunately nobody except us will be able to speak. But we very much encourage you to post questions using the chat function in the right-hand side of your panel. You should have a little box there where you can type in your questions. And then at the end of the seminar, we will save about 40 minutes where we'll try and answer as many of those questions as we possibly can. So please ask your questions along the way. Don't save them to the end, but do that as we speak. So of course, I'm glad to see so many known names here, and so many people have helped us along the way with ETP project since its first edition in 2006. I used to work at the IEA before, that's why I'm moderating this, I guess, today. I managed the 2012 edition, but many of you have been involved in ETP since the first edition in 2006. Of course, ETP is one of the major projects that the IEA does, and I'm pleased to see that the project continues to evolve and it's stronger than ever, I think. So please, Jean-François Gagnier, could you give us just a quick rundown of what ETP is and what it aims to be and perhaps what it will be in the future?
Thank you very much, Marcus, and thank to all for attending this webinar on, as Marcus mentioned it, what is seen as our largest and most ambitious project in terms of energy technology within the IEA. The ETP is the IEA's second flagship publication, and its aim is to really gather all the work that the IEA does in terms of technology policy and research and development analyses to be able to provide a vision to energy policy makers in terms of what can be the role of energy technologies in meeting longer-term energy policy objectives. And so it brings forward information that we gather through our management of our energy technology network that brings together more than 6,000 researchers and scientists worldwide, as well as a wealth of information that we have in our energy databases and our modeling tools to really take a look at what is the state of energy technologies in terms of deployment and performance, but also what could be their role in meeting some of the longer-term objectives. Now, what we is new this year, and ETP 2014 is the first embodiment of a new vision that we've put forward, where we've decided to, instead of our old format of publishing a global overview of all technologies on a bi-yearly basis, we are now moving to a yearly edition that focuses more on specific topical issues that we think are important to bring to policymakers' attention. Now, this mainly stems from two purposes. The first one is to make sure understandable by decision makers, therefore being able to catch their imagination and entice more active participation in the implementation of that vision. That isn't to say that we've stopped doing the detailed analysis that was so prized in previous ETP editions. What we've decided to do now is to divert that information to more online collaborative tools so that we can target those tools to the needs of the people who need the detailed information. But the actual book, the printed publication, is really streamlined to just highlight the key topical issues that are of interest for that specific edition. So examples, of course, in 2014, as you'll hear a bit more later, we've decided to focus on the increased role that electricity will play in delivering energy services worldwide, and you'll hear a little bit more about that. In 2015, we've already started doing work in terms of highlighting the role that energy innovation can play to increase climate mitigation ambitions. And I just came back from the Bonn session of the UNFCCC climate process, explaining to negotiators what we are going to be looking for and already bringing to their attention that aspect. And we've also been discussing and starting previous work on ETP 2016, which will look at the importance of urban energy systems in meeting global energy policy objectives. And so this yearly vision also allows us to plan ahead and start discussions with our partners to make sure that we can have a strong impact into those messages. So I certainly, again, thank you all for being present in this webinar. We are going to be going through a series of presentations on specific aspects of this year's publication, and as I said earlier on, we hope that the online component, including this webinar, can be seen as tools for engagement with partners and people of interest so that you can both ask questions and provide comments on our analytical methodology, but also that you can feel that you can take this information, understand it deeply, and be able to back it up to your own prospective organizations. So with that, I thank you again, and I turn it over to Marcus as the previous author to try to give us an idea of whether he thinks we've succeeded in changing the way that ETP is being presented.
Well, thanks, Jean-Francois. It's well, I do think it's interesting to see this new and more pronounced thematic approach of ETP, and I look forward also to hearing in more detail about this. We'll be going through the chapters. Those of you who already have the book, you recognize the order of the chapters. We'll hear some broader remarks from the ETP project manager, David Elzinga, shortly. Then we'll turn to solar technology, Cedric Philibert, gas, transport, storage, finance, and finally a few words on India in particular, and you'll be seeing a few slides on each and every one of those topics. The slides, by the way, will be available to you on the ETP website afterwards, along also with a recording of this webinar, so you can go back and enjoy it again later this weekend, perhaps. Well, a few reflections looking back in previous editions. I think it's interesting to see the development of ETP since its first was started in 2006, when it was a fairly controversial project at the IEA. Looking at climate change as a topic was in itself quite new. But of course, a lot of things have changed. You know, the solar chapter of this year, I think, is a reflection of one of the most dramatic changes over the last decade, which is the falling costs and much better prospects, I think, for renewable energy technologies that many had expected. Even the most optimistic people, I think, were wrong in many aspects of just how quickly these technologies could penetrate. That, of course, raises a whole slew of questions related to how those technologies should be integrated, one of which, of course, related to storage, what role of storage, also the flexibility that gas can provide. So I think ETP 2014, looking at from the outside, is a true reflection of the most pressing issues that emanate from the development of energy technology themselves and how they fit together as an energy system in this true sense. So with that, I think I'm certainly looking forward eagerly to hearing more of the substance. So please, David, could you give us a rundown of the big picture before we dive into the details?
Great. Thank you very much, Marcus. So I'm going to dive right in to this. The first thing that we looked at is why is electricity important in the global energy system? When we look at it today, electricity makes up about 17% of global energy demand. But when we actually look to the future, we see that growing significantly across all our scenarios. So not just in, say, a clean energy scenario such as the 2-degree but also even if we extend just current trends that we see the demand for electricity growing significantly. But what is interesting is in the 2-degree scenario where we see carbon emissions from the energy system limited in line with IPCC goals to limit climate change to 2 degrees Celsius, we see that across all scenarios, actually, the share of electricity grows to around 25%. What is most interesting in the 2DS scenario is that we see that electricity overtakes oil as the largest energy carrier in the energy system. So it becomes, in fact, the most important energy carrier across the entire energy system. To see this growth in both demand and share of electricity isn't necessarily a positive development. When we look today at the role electricity plays in the energy system, we see that to produce that electricity, it consumes about 40% of global primary energy, and related to that, produces about 40% of global energy-related CO2 emissions. And if we continue on the 6DS pathway, the pathway that is an extension of current trends, that share will largely be the same, but since we'll have higher demand, we'll actually consume more primary energy for electricity production and produce more CO2. But if we contrast that with the 2-degree scenario, we still see that it makes up a large portion of primary energy use, but now only contributes 5% of global emissions related to the energy system. So in this perspective, we see electricity largely decarbonized. But one of the things that we have to examine is we can set these long-term goals, but really, are we on track to meet them? And one of the things that when we look at the high-level picture across the entire energy system, we actually see that we really are not on track except for renewable technologies. And one of the challenges, though, is that as renewable technologies proceed, they are not enough to get us to the 2-degree scenario. We need this broad range of technologies that can contribute to reducing emissions across the entire energy sector. So again, focusing on the electricity sector, what we see looking back again is that we really aren't making much progress in terms of the carbon intensity of the electricity sector. It's been largely flat over the last 20 years. If we truly want to move to the 2-degree scenario, we need to make a drastic change. We need to reduce the intensity of the carbon intensity of the electricity sector, as well as reduce or moderate, I should say, the use of electricity, thereby essentially cleaning up the electricity system. But as I've said earlier, despite the progress of renewables, the ongoing use of unabated coal, especially in emerging economies, is really stopping any demonstration of progress from renewable technologies. So far, I've touched largely on the global context, but of course, when we look at electricity systems and their development, you have to look at that from a regional perspective. And here we show a number of different countries or regions, and what is very clear here is that when you look at the emerging economies, such as China and India, you see tremendous growth. Looking across all economies, emerging economies in the world, we see about an average growth of 145% by 2050. When we compare that to developed countries or OECD member countries, we see a much more modest growth. Averaging across all OECD countries, we see about 16% growth. So this introduces very different challenges. For emerging countries with high growth, we see that significant investments are needed, but therefore a significant opportunity to develop their system in a way that is sustainable. Contrast that with OECD member countries, we see low growth but aging infrastructure. So still more investment needed, but in a context of lower revenues for utilities. So this introduces some significant challenges. But what is clear across all regional electricity systems and energy systems is that the share of electricity is growing in importance. If we truly do want to move from where we are today to meeting the 2-degree scenario, we really need to see a share reversal in how electricity is generated. Today we see that about 70% of electricity is generated using fossil fuels and about 20% is generated using renewables. When we look out to the 2-degree scenario in 2050, we see that reversed, where over 65% is produced from renewable technologies and 20% from fossil fuels. What is interesting in that context is that the fastest growing of the renewables is variable renewables such as wind and solar. And this is going to create some challenges to the way we do things in the electricity system already. And that brings me to flexibility. With that increase in variable renewables, we are going to need to increase the flexibility of the electricity systems. And what we see is that there are a broad range of different ways to do this, whether that's using grid infrastructure, dispatchable generation, storage, or the demand-side integration. And today we're going to touch in detail on dispatchable generation, primarily gas technology in this context, as well as storage. But those other two still are equally important, using the grid to link different markets and different systems, as well as using the demand side to reduce, to increase flexibility. And that is, I'd say, the demand side is one of the most underutilized today in the electricity system. Now I just want to move briefly over to the demand side. So far I've focused largely on the generation side. What we see is by decarbonizing electricity, we have a spillover effect into the demand side. The most, I'd say that the most demonstrated one is in the building sector. Today the building sector consumes about 50% of global electricity demand. So from that perspective, if we can decrease the carbon content in that electricity, we automatically decarbonize energy use in the building sector. And from that perspective, if we increase electrification in buildings, buildings themselves can become cleaner as the electricity system is decarbonized. We also have done some interesting analysis in the area of transport, but I'm going to leave that to the transport expert to cover in one of the next parts of this presentation. So lastly, what I want to touch on is that when we look forward and we want to create a sustainable electricity system, we see that this is one that is smarter, that is multi-directional, and is an integrated energy system. And this requires significant, I'd say, increase of integration of technologies across the electricity system, and doing this with a much more longer-term perspective. So this, of course, long-term planning is done today in all electricity systems in the world. But to look towards the sustainability goals in a much more targeted fashion will bring tremendous climate benefits, but also economic and energy security benefits. And one of the things that we've been touching on more and more in our analysis is to look at the use of energy from a services perspective. So what are the services that that energy is providing, whether that's lighting, whether that's heating, whether that's mobility, rather than looking at the energy itself. People don't use electricity. They use the services that electricity provides. So looking at it from that perspective can really bring new insights on how we can develop that. So thank you, Marcus. With that, I turn it back over to you.
Thanks, David. As I mentioned, I think one of the most interesting developments over the last few years is the dramatic fall in costs, and I think in particular that concerns solar. And one of the people at the IEA who's done the most analysis on solar technologies is Cédric Philibert. And Cédric, could you please take us through the solar chapter of ETP, because I think this is the first time that the IA actually integrates a deep analysis on solar in one of our major scenario projects. So Cédric, please, the floor is yours.
Thank you, Marcus. I'll be happy to walk you through this chapter rapidly. The key findings are as follows. In the 2DS, the solar electricity comes close to wind power, hydropower, and nuclear power by 2050 as the four pillars of almost fully decarbonized power sector. But we have been also looking at the so-called higher-end scenario. The higher-end scenario is how do we achieve the 2DS if nuclear power and carbon capture and storage, for whatever reason, cannot develop as they are modeled in the 2DS. Can the renewables fill the gap? And the answer is basically yes, and it's basically almost only the variable renewables which have unlimited potential that come to fill that gap. And solar then becomes, in fact, the first electricity sources as early as 2040, and by 2050 it provides over a fourth of global electricity. But that's not only photovoltaics, as anyone believes, it's also solar thermal electricity. And this chapter tries to show how both technologies complement each other. But of course, as you said, Marcus, the important thing in the last few years was a rapid decrease of the cost of PV modules. PV modules have seen their cost divided by 5 in 6 years. And when you look at the entire PV systems, you see that in most mature markets they have declined by a factor of 3 in those 6 years, as shown here with Italy, a sample of thousands of systems of various size, and you find this factor 3 almost everywhere. But one of the consequences is that grid parity is reached in some countries, or maybe we should say socket parity, that is for households, but most importantly perhaps for some commercial buildings, some small industry buildings. The PV cost is now lower than the retail prices for electricity, and this gives, of course, a strong impetus into the development of PV systems as a cheaper solution for people to get their electricity. And you see here how in just 3-4 years, from 2010 to 2013, in Germany, Italy, and California, the range of levelized cost of energy has come down. Either the average cost of retail, the average retail electricity price, or the price for some of those who consume the most. In California, you have the various tiers, and the LTO price of PV is lower than the highest tiers, the highest retail prices for those who consume large amounts of electricity. Now you also have these solar thermal electricity technologies, the CSP technologies, which offer a different ways of making electricity in places where you have very good direct normal irradiance, very good sunshine and clear skies, and then you have a bunch of technologies that allows to generate electricity after you have collected the heat. And this is very important because it gives an opportunity to store the heat before turning it into electricity. And this is a form of storage that is very good because first, it's very effective, there are very few losses, and second, it allows to increase the capacity factor of the conventional part of the plant. So at the end of the day, it does not increase the cost of electricity, but it can even reduce it a little bit. Most importantly, it increases its value in allowing to generate electricity on demand, and especially during peak times. In most countries, peak times, they can be in the afternoon, but they are more important after sunset. And when you have big population of PV system in a country, then the net demand peaks after sunset, and therefore solar thermal electricity from CSP plants will be able to compensate and inject more electricity in the system at those times when the sun is not here. So let's have a quick look at the solar deployment in the 2DS. It's quite amazing. It goes to 11% for PV and 7% of annual electricity for solar thermal electricity. You see also that PV develops faster because today it's much closer to competitiveness than solar thermal electricity, but also again because it's after PV has been deployed that the need for dispatchable solar electricity when the sun is not here anymore appears more clearly. An important thing on PV is that China leads on PV capacity. It leads the market since 2013, and it will continuously lead to 2050 and be a very important player in that. And you see the growth of solar thermal electricity that comes really takes over after 2030 when costs have been reduced and when the need appears obvious. Now in the higher end, the numbers are very much more important. It goes up to 16% of global electricity for PV and 11% for solar thermal electricity, and that's why together they become the first source of electricity. Again, China plays a big role for PV, but for solar thermal electricity, it's more evenly spread out between the US, India, Middle East in particular. And this we'll see again here when you see for both scenarios or both variants of the 2DS, the standard 2DS and the high renewable, that the combination of PV and CSP varies according to the quality of the direct normal irradiance. So where it is excellent, that includes Africa, North and South Africa, Chile, Mexico, and Middle East, solar thermal electricity will eventually dominate everywhere else, even if you have some areas, southwestern China, southwestern US, western China, parts of India, you have areas available for CSP plants and solar thermal electricity, but still PV dominates in these countries the mix. PV system costs will be further cut, and we have reasonable hope that this process will continue. Of course, it will not be as fast as it had been in the last 6 years. This was historical, and now PV modules have roughly stabilized for some time. We expect that new technical improvements will further reduce the cost of modules. What we see is that the system costs continue to decrease when markets mature, because a large part of these costs are local, and when a local market matures, then these costs are reduced by learning, scaling up, and density of projects. And this is true for both utility scale and rooftop PV. Half of the PV will be distributed, will be basically on rooftop. Of course, self-consumption will be a driver, and because it's limited by the match between availability of the resource and the presence of the demand, especially for households, we expect that some distributed storage will also find its economic role, as it has to compete with retail prices and not with the wholesale price of electricity. Load management, as David already mentioned, also is an important tool that can help increase the share of PV generation for customers. CSP plants will also have their investment costs coming down. We see now an emergence of a bunch of new technologies, towers in particular, but also linear Fresnel are coming in, and we expect they have a great potential for reducing the cost of the technology in the coming years. So here we have tried to show how both technologies will complement each other with this typical day model with 18% PV and 12% or 24% solar thermal electricity, and here you see how they will rearrange the merit order of the various technologies, but you see basically how solar thermal electricity comes in the starting in the afternoon and extends up to midnight basically to generate electricity when you have this big peak where in some countries already you are calling for oil products, and so you already have competition in interesting terms for solar thermal electricity. Variability has been mentioned by David. It's a true challenge, and I won't repeat what he has said about the various options to increase the flexibility of the systems. Just to I want to signal that we have been publishing a full book on this, which is called The Power of Transformation. I invite you to look for it on the IEA website. And it shows that even if you have up to 45% of variable renewables, there will be an increase in the cost of the rest of the system, but this increase will limit the total increase, even if wind and PV costs were to remain what they are. The increase in the rest of the system will be limited thanks to a lot of options for flexibility, including other renewables, including interconnection, including load management, of course, and of course friendly renewable energy deployment, number of options. So let me conclude with some recommended near-term actions. There is a problem with the current market design, which may not provide adequate remuneration for solar technologies. They are very capital intensive. Everything has to be paid upfront on day one, and this makes it difficult to get to earn a fair return on investment if you have lots of uncertainties on markets. So you need to have a stable framework. Financial incentives remain needed in most markets to compete with existing generation, even if the cost gap is now much smaller. Long-term power purchase agreements are one option, but there are other options to be looked at, in particular for distributed PV. PV will be in part driven by self-consumption. This raises issues about the recovery of grid costs, and this topic has to be looked at very carefully, because we will need grids in the future. We don't believe in a world where everybody has its own PV plant and that's it, and there is no need for a grid anymore. We believe to the portfolio of options, and grids are the way to make this portfolio live together in electric systems. So this is a serious issue which should not prevent deployment of distributed PV, but has to be considered and addressed. And finally, the remuneration of solar, in particular solar thermal electricity, should reflect its time value and also the value of the other ancillary services it may provide. And this is the right way to go to make it deploy more rapidly, but in a sound economic context. With this, Marcus, I think I'm done. I'll be happy to answer any question that might come in the future in the coming hour on this chapter. Thank you very much.
Thanks, Cedric. This is super interesting. Yeah, I see lots of questions are coming in, so please continue to post those, and we'll do our very best to answer as many as we can towards the end. Of course, gas is another area. Natural gas, the development in particular around unconventional gas. I think few of you have missed the attention that the IEA has been giving to that area. The IEA sees at least two really important roles for gas in the context of a more sustainable energy system. One being it replacing coal-fired power generation in particular, thereby reducing emissions. And secondly, which ties nicely into what we just heard from Cedric, is regards flexibility. So natural gas could enable a higher penetration of variable generation, such as solar. And I think we'll now hear from two of the lead authors of the chapter on natural gas on those very topics. So please Sean McCoy and Simon Bennett. Could you take us through the chapter on natural gas?
Thank you very much, Marcus. I can't go without, of course, thanking my co-authors, Steve Heinen, who will also be speaking in a moment, and of course, as Marcus mentioned, Simon, because they aren't the only people, or I'm not the only person who's involved in this, and of course, if you don't like something I'm saying, you should blame everyone equally. Anyway, as Dave mentioned in his overview of the 2-degree scenario, electricity demand nearly doubles and supply is largely decarbonized. And as he mentioned, this is because the opportunities to decarbonize electricity from an economic perspective are really big and have a big impact from the spillovers. And so this happens, as you've seen a lot, especially from the previous presentation, through the addition of variable renewable resources to the system. But there's a lot of other things happening too, so I'm going to take a look at those. One of the things, as Marcus mentioned, is fuel switching. So initially, what you see is fuel switching from coal-fired plants to gas-fired plants. And this figure that I'm showing has the intensity of electricity generation for different regions of the world in the 2DS scenario over time. And the light lines, hopefully you can see them, indicate the emissions intensity of best available technologies for coal and gas-fired generation. And so you can see that for the most part, the emissions intensity of systems now and in the near future are above that of gas, so we can switch to gas to reduce emissions intensity of the system. But then as we move forward towards, say, 2030 or so, the emissions intensity of the average system starts to drop below gas. And so the switching from coal to gas or the addition and the addition of further gas can actually help you reduce emissions intensity any further, and you need to start moving towards CCS. And as I said, this happens much sooner than I think many of us had thought in the 2DS, and that's around 2030 for most regions, and earlier in some. And the other challenge with the penetration of variable renewable resources, or VRE, is that dispatchable generators, such as coal and gas-fired plants, but also others, will have to respond more rapidly to changes in output, some of which, no matter how good we get at predicting, will still take us by surprise. And so this figure shows output from the same combined cycle gas turbine unit in 2 different years, one in yellow and one in green. And the notable difference in output between the two is strongly reflective of increasing penetration of renewables in the system in which this unit was placed. And so that highlights the 2 key roles which Marcus mentioned for gas-fired generation in the 2DS. One is to reduce CO2 emissions from thermal generation by switching from coal to gas, and eventually with the addition of CCS. And the second is to support the integration of variable renewables by providing flexibility services. And I'm going to focus for the next few slides on the first topic, that's the fuel switching. And so in the book, as was mentioned at the very beginning by Jean-François, we focus a lot on technologies. And so we've gone through a list of power generation technologies that use gas, and taken a look at them from the perspective of their maturity levels, their performance, and their capital cost, as well as other important attributes. And I'll be talking about those a little later. But what I'd like to focus on this slide are just 2 of the technologies that are important for baseload power generation currently, and what we think in the near future. And that's combined cycle gas turbines, CCGT, and combined cycle gas turbines with CCS. And these are very attractive because they have very high efficiency and, relatively speaking, low capital costs compared to other options, such as coal-fired plants or nuclear. And so these are very attractive options. Of course, the challenge is that the price of gas is highly variable and uncertain. And this slide shows 4 different regions for different gas prices and carbon prices where certain generating technologies provide electricity at the lowest levelized cost. And so today, coal prices for internationally traded hard coal are around, let's say, $80 or so a ton, or $3.5 per million BTUs, which is around where that lower blue line, dotted line is in the figure. And what you can see is if you look at gas in Europe, which is maybe $10 or $11, you're just on the coal side, in the coal area of this figure. And however, as CO2 prices increase from the very low level that they are today in Europe, you can find yourself fairly rapidly moving into territory where combined cycle gas turbines start to be the lowest cost option for producing electricity. And if CO2 prices were to continue to increase, into a world where combined cycle with CCS starts to make sense. On the other hand, in the United States, where gas prices are very low, today being $4, let's say, dollars per million BTU, you're soundly in a region where gas makes a lot of sense for new build, and surprisingly low carbon prices can deliver CCS on gas. Of course, there are other factors that come into the mix when you're looking at investment decisions that are beyond gas and CO2 prices. Let's not kid ourselves. And these factors are things such as environmental regulations on conventional pollutants, water constraints, deregulation or liberalization of electricity markets, and of course fuel supply concerns. The interesting thing, however, is that most of these issues, with the exception of around fuel supply, typically tilt the balance toward gas and away from coal, for power generation anyway. But of course, fuel supply is obviously a very major one, as we've seen in Europe recently, and can really make a challenge to getting more gas for power generation. But I think the key point here is that at gas prices below $8 or let's say $10 per million BTU, gas tends to be a preferred option, and that increasing CO2 prices will make gas look increasingly more attractive even at higher gas prices. And this starts to play out in the 2-degree scenario, where by 2050, excuse me, we see about, well, just over 40% of power generated from gas-fired plants coming from plants with CCS. So these are gas plus CCS plants. And this is particularly prominent in the OECD, as you can see from the figure on the left-hand side of this slide, where the dark orange and the light green represent gas-fired generation with CCS. And as you can also see, which starts to tie itself together with the figure I showed you about carbon intensity earlier, when you look at the right-hand side, you can see that the real growth in power plants, gas-fired plants with CCS starts to happen in the 2030 to 2040 period. And another interesting fact is that you see that the capacity factors of the plants equipped with CCS is much higher than those that are not equipped with CCS, and that means that a lot of that gas capacity, unabated gas capacity built into the future would be for probably more peaking units, really to supply some needs, some flexibility in the system. So that takes a look at the first issue, that's the fuel switching from coal to gas, and now I'm going to spend a few minutes taking a look at the second issue, and this is the idea that gas-fired generation can work to support integration of variable renewables by providing flexibility services. So we'll dive into that. Again, looking at technologies, I mentioned we looked at a variety of them on a number of different parameters, but one of the things I really would like to drill home is that it's not just about efficiency. That's something that I've mentioned here quite a bit, but it starts to become about other attributes of the technology. I'm going to talk about that more in a moment. But the three technologies I'd like to focus on now are combined cycle gas turbines, open cycle gas turbines, and internal combustion engines, or ICE. And the benefits of these technology are that while being efficient, they also have very rapid startup, rapid ramp rates, and other things that are very important when you look at flexibility, as well as being relatively inexpensive. And when we say flexibility, what do we mean? Specifically, we're talking about the extent to which an electricity system can adapt the pattern of generation and also consumption in order to balance supply and demand. And of course, an electricity system, when you have a mismatch between supply and demand, you have variations in voltage and frequency, which can impact reliability of the system. And historically, the variability of demand and the reliability of supply have been what have driven the needs for flexibility. But as we move forward, as Cedric was mentioning, the integration of variable renewals will start to drive needs for increased drive increased variability of supply and needs to take actions to make sure we can maintain the reliability of that system. And the factors that we look at when we're talking about technologies to meet these flexibility needs are things like startup times, ramping capabilities, and turndown ratios, in addition to the more conventional metric of efficiency. And so if we look at that and we take a look at our comparison of ramp rates, turndown ratios, and startup times, we can see that in particular combined cycle gas turbines, open cycle gas turbines and internal combustion engines, that's OCGT and ICE, have relatively high ramp rates, low minimum turndown ratios, and short startup times, all things that we'd be looking for to support flexibility in the system. And of course, one of the challenges is that rounding these plants more flexibly will have an impact on the cost of operating and maintenance of these plants, and that's something that we need to be thinking about very carefully. And it's also important to note that we do show coal on this chart, because coal is a technology that, from a technical standpoint, can, in many cases, supply the sort of flexibility we need. However, it's hard to see how one would make an investment in a relatively expensive, capital-intensive technology when you have a lot of uncertainty about how it might be run. So in conclusion, I'm going to cover all the conclusions, I think, from the chapter, but I haven't talked about them all here, so I'll give you a snapshot, and I hope you'll go to the chapter to see more. First, natural gas we see as a key transition fuel, both as part of the means to decarbonize power generation, but also to support the growth of variable renewables. We also feel that both coal and gas can provide for baseload and flexible power using existing technology. However, both these technologies will be hit with increased operating and maintenance costs by ramping and shorter startups and more flexible operation. And at the same time, there's going to be more uncertainty in operating hours that makes investment decisions more challenging, and in general is going to be a challenge to high capex technologies. So what we see are policies that regulate CO2 or price CO2 can help favor gas over coal and actually help with flexibility in some sense, and also a need to reward system benefits, as was mentioned in the previous presentation, of, in this case, for flexibility. And these sort of policies become critical to delivering the 2-degree scenario in the future. So that wraps up what I'd like to say about the gas chapter, and I'll hand it back to Marcus. Thanks, Marcus.
Thanks, Sean. That's a brilliant rundown of the chapter, I think. So now to something slightly different. Not completely different, but slightly different. Let's turn to the demand side. ETP 2014 has, I think, a firm focus on demand side on transport, and given the theme on electrification, it's natural that we will be hearing a lot about electric vehicles and electrified transport more generally from one of our lead analysts on that topic, Mr. Tali Trigg. Tali, the floor is yours.
Okay. Thank you so much, Marcus. Again, my name is Tali Trigg. I'm a transport analyst here at IEA. From ETP 2012, as Marcus and JF, I gave a bit of a background. We had more of a broader focus on the whole sector. There was even a hydrogen chapter. So as part of this 2014 thematic focus on electricity for transport, unsurprisingly, we're looking at electric vehicles. What's different in this chapter, a bit unique, is that instead of just looking at passenger electric vehicles, which have received a lot of attention, we've looked across all modes and also across all charging and recharging options. So I'll be taking you through that a little bit. Broadly, you could frame it in, the chapter could be framed in what, where, and when. So what should be electrified? So that includes, as I mentioned, a broader look at vehicle electrification across all vehicle modes and technology configurations. Where does transport electrification make more sense? And part of that question is also when will that happen? So within this, we're introducing a variant of the 2DS scenario called ET, electrifying transport. So similar to the solar high REN scenario, this is looking at what happens if we take electricity to its maximum. Also looking at a time frame for e-mobility deployment across different regions. And then finally, the impact on energy use and CO2 emissions versus the 2DS, so seeing what the difference is. Sorry, 1 second. Oh, sorry. There we go. Okay, so from what David showed earlier, he was pointing out a 2DS share reversal of electricity generation by 2050. What I'm showing you here is a little bit, let's say, the bad news, or the last 40 years. So from 1973 to the present, you can see the dominance of oil in transport and increasingly how much transport accounts for oil supplies. So really, not much has changed in this sense, except that transport remains the end-use sector with the least diversification in terms of fuel. If we elaborate on that and look by modes, you can see here from 1971 to the present, more or less, different modes in terms of energy consumption. And what you see is that the road sector dominates. And unfortunately, it seems that the most energy-intensive modes are the ones that are accounting for more and more energy consumption. So that includes such things as passenger cars, light-duty vehicles, and of course aviation. What you see here is at the bottom, the most energy consumption takes place as road, as I mentioned, and the total energy use grows from less than 50%, just half in 73, to almost 3/4 today. So this techno-colored image is not meant to just daze and confuse you, but this was sort of a first slide, a first attempt to understand electrification of all vehicle modes, what's more appropriate, what's mature, where the savings are in terms of economic potential. So we looked at everything from, say, two-wheelers, passenger cars, trucks, buses, rail. What you don't see here is air and shipping, because we just didn't see a lot of potential there in terms of, let's say, economic potential and technological maturity, though there certainly are several niche applications. And here I'll make the distinction between a vehicle that's electric and a vehicle that's electrified. So for example, an airplane could today be hybrid electric, or it could be more electrified, onboard electrification, or even ships. That would be different from it being electric, so actually powered by electricity. So that's more the focus. That's the focus of this chapter here. And what you see is, for example, for two-wheelers, there's 150 million electric two-wheelers in China today. So that's quite a huge number of vehicles, a huge market share. In fact, half of all two-wheelers in China, motorized two-wheelers in China, are now electric. Looked at passenger cars, so you're familiar with everything from small battery electric vehicles, such as the Renault Twizy, to larger ones, such as, say, the Tesla Model S, to plug-in hybrids, such as the Chevy Volt. Unusually, we looked at trucks, which there hasn't been too much work on this, so there's a big focus for us on the freight sector to try to understand how far can the road freight sector be electrified. And what you see there is there are delivery trucks that can be fully electric, and then for heavier trucks, however, there are more challenges, technological challenges. So we tried to see what the state-of-the-art is in terms of induction and catenary, so overhead lines, for example. I'll get back a little bit to that on the scenario results, but just to give you a broad overview. So if we look today, what's the situation today? What we see is that electricity use represents less than 1% of the energy use in transport. Most of that is going to rail here, as you see in the slide, though thanks to the efficiency of electric freight, 3.7% of total freight ton kilometers are represented through electric freight. And if you look at progress over the last couple of years, you see that rail electrification is moving forward across all 5 metrics here, both infrastructure, tractive stocks, cars, TKM, so for freight, passenger kilometers, and then just energy consumption. There's been more relative progress for passenger rail than for freight rail. If you look at road freight, which again is this is more of a more in the realm of thought experiment and trying to understand what we do know and don't know. What we're seeing here is that it's the concentration of heavy-duty truck traffic on highways. And what we see is in France, for example, 50% of all heavy-duty truck traffic goes on 2% of highways. So there's a huge concentration. Where in the U.S., 40% of all heavy-duty truck traffic takes place on just 10% of highways. And for all the countries you're more familiar with, you can imagine, be it Canada, Sweden, you can see there are certain arteries, there are certain corridors where freight is concentrated. So if that's the case, are we looking at, if we are electrifying, say, highways and putting catenary lines, we may not have to be talking about 100% here, but maybe you can get economies of scale, you can get quite a bang for your buck for the first, say, % or two that you may want to electrify. Of course, this has equal implications for hydrogen, natural gas, you name it. If we turn to the scenarios a little bit here, so this is the 2DS ET scenario, the high electricity variant for transportation. You see electricity demand on the left side and then transport energy consumption on the right side. As it says here, electricity for transport demand accounts for just 13% of total electricity demand by 2050, despite electrifying over half of the passenger vehicle fleet. So this is in large part due thanks to its efficiency. So how does this differ from 2DS? Well, in 2DS, we had done a lot on electric vehicles already. So two-wheelers and cars were already quite electric, and rail, of course. Two-wheelers are very important in terms of numbers, but not in terms of energy use and CO2 emissions, again, because they're quite efficient. So the emphasis really here in 2DS ET is on electrifying heavy modes, and within that, really freight. Another subsection of that is bus electrification, so not freight, but public transport. And what's really interesting about buses is they're probably the most dynamic when it comes to how you can charge them. So they have, you could argue, the highest maturity by different charging options. So you can charge them slow, fast. There's battery charging, there's static induction, dynamic induction, and of course overhead lines. Finally, so if you look at the CO2 emissions impact, so this is for the transport sector and the needed CO2 emissions to get us from 6DS down to 2DS. So of course you see the most dramatic CO2 emission savings are from 4DS to 2DS, and there's a little more coming from 2DS ET. One, I suppose, interesting finding is that in our modeling, by focusing on electric instead of hydrogen, electricity demand ended up remaining more or less the same. And part of the reason for that is because of the inefficiency of producing hydrogen, which is more of an interesting modeling result, but it was something we're trying to understand. How would electric demand change? Would it be dramatic? And the answer is no. Oh, sorry. So with that, without skipping to the next presentation, thanks so much, and I'll turn it over to Marcus.
Thanks, Sally. Again, very interesting. It's cool to see those numbers of just how concentrated freight transport is, and you know, I think that turns around a lot of the arguments that's being posed around, for example, the potential to electrify transport in many countries. So let's move on now to one of those sources of flexibility that Dave mentioned in his introduction, namely storage. Sometimes storage is kind of portrayed as one of those potential solutions that could dramatically change the game. If only we could store electricity, some people argue, a lot of the problems that we see around, for example, solar and wind, and its ability to their ability to penetrate the market much more quickly would be solved. Is that true or not? Let's hear it from Steve Heinen, who I think is joining us from Dublin, and Luis Monuera, two of the authors of the chapter on storage in ETP 2014.
Good afternoon, everyone. I'm Luis Monuera. I'm an energy analyst here within the ETP division. And yeah, so myself and my colleague Steve Heinen, we're going to present specifically on the role of storage, specifically in future electricity systems. So here, the first slide we want to show, this really highlights our scenarios for electricity generation. So on the top slide, we have on the top part of the slide, we have the 6DS, which is our kind of business as usual scenario or worst case scenario. And on the left, we have the electricity generation by source. And then on the bottom, we have the 2DS. That's a scenario that gets us a 50% chance of staying below 2-degree increase by 2100. There we have, again, the electricity mix on the left. And on the right, we have a more aggregate version for 2 time slices, 2011 and the end goal, which is 2050. So in our scenarios, all regions see an increase in the share of renewables on a global basis. As Dave mentioned earlier in the presentation, the 2DS shows what we call a reversal in the way electricity is generated today. Today we have nearly 70% of electricity generated from fossil fuels, and 20% comes from renewables. And the 2DS we see in 2050, 65% will come from renewables and 20% from fossil fuels. Now, in particular, what I want to focus on, which is what's really relevant for storage technologies as a key driver, is that under this reversal, what we see is the greatest growth coming from variable renewable generation, specifically wind and solar, which account for 30%, 35% of the electricity generation in 2050. Now, this slide has already been presented by Dave, but it merits showing again for this chapter. For this increased deployment of variable renewables requires an increasingly flexible electricity system, and to cope with this, we have 4 key options aside from better operations. The first one is reinforcing or expanding the electricity grid infrastructure to increase the balancing areas of the system. The second is increasing or moving towards more dispatchable generation, of which fossil generation is the main resource, but it's not the only one. Then storage, which is our focus for this particular section of the webinar. This has been receiving great attention in many circles, as Marcus highlighted in the introduction. And finally, of demand-side integration, which has a great potential as a low-cost flexibility resource, but over which some uncertainties exist. So in ETP 2014, we have already heard on the role of flexible electricity generation in the form of the natural gas chapter. And now we're going to focus more on electricity storage and to some extent on demand-side integration. So at present, storage capacity is dominated by one single technology, pumped storage hydropower, pumped hydro. Current pumped hydro capacity is less than 3% of global power capacity. It's around 140 gigawatts. Most of it was built, you can see below, the build-up of pumped hydro capacity over time since 1960. Most of it was built to help manage inflexible nuclear plants, but pumped hydro plants are still being built. There's around 24 gigawatts of pumped storage plants planned in the next 10 years, and this is mostly in China, in the US, and some in Europe. Now, the majority of the existing plants are, for the most part, amortized assets, and they mainly sell in wholesale markets, and they exploit electricity price arbitrage opportunities. Other power storage technologies that you can see on the top right, they're very marginal, and they're globally, in terms of installed capacity, just above 1 gigawatt. Now, as more variable renewables like wind and solar are deployed, there will be a greater need for the grid services that storage can provide. Now, in these applications, storage competes with other technologies like flexible thermal generation, demand response, or better grids, which, depending on each particular system, might be more desirable or cost-effective. So this is one of our key messages for storage analysis in the CTP, that the future role of storage really is defined according to its applications. Storage technology is not a single technology, it's diverse, and they're a very complex set of technologies. And the role really cannot be understood without taking a system perspective that has appreciation for the service and the applications it provides. So the main reason behind this is that there's 3 key factors that affect the economics of storage. The first one is the volume of energy stored, or the duration of the discharge of the stored energy. Second one is the power requirement of the application. And the final one is the number of cycles, or the utilization of the device. And finally, there's also the location. Where is the storage asset in the electricity system? Really important, first of all, for assessing the role of storage in specific systems, but also for designing policy support and for directing innovation and R&D. Now, the straightforward analogy that we have in this slide is the pumped hydro plant. Just to keep this in mind through the presentation. The volume of energy would be the size of the reservoir, which would have specific costs, which are related to the excavation, to civil engineering works. Now, the power costs are related to the turbine capacity and the altitude difference between the two reservoirs. And again, those are different drivers for the cost. For a pumped hydro plant, perhaps the frequency of storage cycles has less of an impact on cost, but for some technologies, a key determinant, for example, for batteries, it's a crucial factor. We have relatively short cycle lives, and this means that sometimes replacement costs have to be added. And finally, the location is really important here, for example, for some technologies like pumped hydro or perhaps compressed air energy storage, which is mainly done in underground caves. These technologies can be very constrained by their location. So I will now pass on to my colleague Steve Heinen to continue the presentation.
Thank you, Luis. One of the things we've been stressing is to really take an application perspective, because as Luis illustrated it with the example of pumped hydro storage, this technology was built for a reason. The reason was that nuclear was basically a baseload technology running flat through the day, and we needed that the energy requirements during the night, for example, was lower than the nuclear energy produced. So there was a normal market opportunity to store cheap nuclear energy during night and discharge it at peak prices during day. So arbitrage opportunities has driven most of the storage deployment over the last 40 years. But what is obviously clear today is that there might be a second wave of storage at the horizon. I mean, this is driven by a few trends in the electricity system. So first of all, we have penetration of variable renewables, but you also have an end-use electrification. So there might be opportunities to provide operations support, but also system planning applications from storage. So drivers are though very system specific and obviously very complex. These depend from market, regulatory, but also technology development, and eventually obviously local geographic conditions. So that means that it's very difficult to give a general assessment of storage. Though we try to come up with a certain categorization to explain you a little bit more that storage is not just, first of all, a single technology, but is composed of a multitude of technologies. Each has specific characteristics, and each can meet specific applications. On this graph here, we're showing you the applications for storage on the left and the technologies on the right. The applications on the left are typical power systems applications that are already provided by system operators and others in current systems. So these are not necessarily new, but certain trends, as I did before, might make those applications more important and might create a new need for storage. This obviously goes combined with a smartening of the grid or the penetration of IT systems that allows it generally to control more distributed assets throughout the system. So you'll see here that we have a need for technologies that provide very short discharge durations and that it might be a little bit more smaller in scale. Those could be typically provided by more technologies like supercapacitors, flywheels, or batteries. Those technologies have also high energy specific costs. So that means if you want to store a lot of energy, so a lot of kilowatt hours, they get very expensive and uninteresting right now. So we use other technologies for those things, which would be more on the top right corner for arbitrage, interseasonal storage, or even seasonal storage. So namely, that would be pumped hydro storage, PHS, compressed air energy storage, CAES, and a hydrogen storage. Very important is also to note the siting of those technologies. Some might be on the generation side, other might be connected to the grid, and others might be directly with the end users. So now, if we drive this analysis further, what we've done is to compare storage not just by its cost itself, its capital cost, but more importantly, so its performance in the system. So that means the levelized cost by using electricity, so charging the storage, taking into account the storage cost, and finally the discharge cost, to give us a little feeling about how actually storage technologies compared to your current price setters in the systems. So it's obviously very important that storage will never be deployed in isolation. They will operate in a system, and as I said before, many of these applications are already provided by generators mostly, but also by the grid, and increasingly through demand-side response, even from the end-use sectors. So for each individual applications, we assessed here the cost for different technologies for both today and in 2030. So you see that the cost today is always the orange graph, and the cost in the future is the blue one. And we're looking in detail for the potential for cost reductions. So this will now be for different applications. As I said, there's 6 applications here. Some are more interseasonal storage, so very long-term storage of large quantities of energy, compared to more grid services like load following and frequency regulation, which tend to be very dispersed throughout the system, have many cycles per day, and also tend to be small, as I said, more distributed. So maybe more on a let's say 10 to 100 megawatt scale, already pretty big though. So as you see here, if we look, for example, at something like inter-seasonal storage, which currently is basically provided, if you want so, by fossil fuels. You can store coal, gas somewhere. It's relatively easy compared to electricity, and you use your electricity your power plant to produce electricity when you need it to the season. So if you compare all technologies, pumped hydro storage, hydrogen production, compressed air, they will be also a lot more expensive. So we do not see an opportunity there. If we look at though what is happening already today, kind of the daily price and arbitrage, or even the T&D investment case, which is a 5-hour storage, 100 megawatt, there you see that those kind of large energy storage technologies could be cost competitive and are effectively, if in the example of pumped hydro storage, cost competitive. As Luis said, there's 25 gigawatt of storage, of pumped hydro storage under construction currently. But it is very clear that even in the long term, everything which is more battery or distributed storage is, even for these applications, and even our positive assumption, not cost competitive. Those technologies have a role to play though as well in the storage landscape. Their application is more on the smaller scale and high frequency events, which is like load following, frequency regulation, which are either provided today through automated generator control, or on the other case, mainly just through markets, in certain markets, obviously. And then finally, off-grid applications. There was obviously a need for some off-grid applications in using storage, where their storage is basically without where the only competitor is obviously using a diesel generator, which is very expensive. So this is probably less an OECD case, but in many developing countries, this is a very important application, and the potential of storage there is obviously big if we reach some technology development as we foresee it here by 2030. So a big application to look out for. And obviously I should not forget here to mention, obviously we see this already happening at very, very small scale with, for example, advanced electric lighting devices in rural areas that have been deployed largely. Those are low-cost applications, and their electricity has already shown its potential to improve quality of light by something as simple as lighting. If I go to the next slide, I want to also discuss a little bit the vision that we see in store for storage deployment in our different scenarios. So as I said before, storage is obviously very context specific, and it depends on the market and regulatory framework, but also on the competition to other technologies, so or other flexibility means. So what we've tried to assess here is to show you that the storage penetration for our 2-degree scenario, which is shown here in light green. So there you see that storage, as we will see, goes up in all scenarios, because at one point we see certain arbitrage opportunities there for storage. But what we also try to assess, what if we see a certain breakthrough in storage, so really a very strong reduction in cost. And yes, of course, this doubles our installed capacities, but we need to say that even this even this penetration is still, from a power systems perspective, small. We're talking in all these cases about less than 5% of installed generation capacity. So this goes back to say that for us, storage is important, of course, but it is not going to dramatically change how we perceive power systems. What we also try to analyze here is the potential of electric vehicles. As my colleague Tali Trick pointed out before, is obviously electric vehicles are, from a transport point, very interesting, but they're also a consumer of electricity, but ultimately they can also provide services to the grid. So here we assess basically the potential of these EVs to provide demand response. Obviously we considered here to a certain amount the user acceptability. I mean, nobody will be ready to accept that its car won't be charged if he needs it. So we kind of limited the potential of these technologies, but still we see that EVs can really seriously reduce the storage amount. So that obviously has positive impact in terms of space requirements and also investment requirement, and also makes the case for EVs better. So again, system thinking and systems integration is key in delivering these new energy systems and based on electricity that we're discussing here. So let me now go to the next discussion, which is, as I said before, is the market. I mean, one thing we shouldn't forget is that if we want storage to be built in most OECD countries, that will mainly be in unbundled electricity systems. So it needs to have a business case for any private investor to start putting money in there and also have a return on the investment. It is very complex, as we said, to assess or to give any general comments on storage profitability, because as we said, it's obviously a function of electricity price you're using for charging. It's a price of the spread then at which you are discharging. It's also important is also the technology capital cost, and in that it's very important to say that certain technologies might benefit from spillover effects, from learning effects in other parts of the energy systems or even non-energy systems. I mean, the EV development obviously has brought already down battery costs a lot. So if you're thinking about using batteries for load following or any of those applications, that could likely be further development of kind of the technologies we have in EVs today. So very important market to look at there. Another key issue is obviously the ownership of storage. As I said, under unbundling, transmission or distribution system operators are allowed to own any generation. As storage is often treated as kind of a generation technology, that means that most of the transmission and distribution system operators cannot own any storage or cannot use any storage in that way then to benefit the whole system or to provide stuff like controllability or other means. Or even a very important asset that we discuss here is the benefit stacking. An important thing of electricity, mainly electric storage system, that they can provide obviously many of these applications that we discussed before. So we could have a case where the storage asset could provide voltage regulation, but could also provide load following. So that would make the benefit would make the business case more interesting. Problem is obviously that if you have a generator, if storage is treated as a generator, it's very difficult to just reward these systems based on penetration like that. So it's a very difficult case that where regulatory research in regulatory frameworks is essential to really develop a framework that is able to capture the full benefits on storage. Another fact is that a big advantage of many of the more distributed storage devices is their controllability, responsiveness, and also modularity. And again, here the market and regulatory frameworks are very important if we want to capture those benefits. So rewarding how fast and how often assets report is very important. Again, within the lines of system integrations, I think it's not so far we discussed really we discussed really issues around storage around the power system. It's obviously though that if we make the problem bigger, we might have more options to store. So by that I mean systems integration. So not just looking at storage opportunities within the electricity system, but looking at the heat system or looking even at the gas system to have opportunities to store excess electricity and make a maybe develop a pathway that is that's easier to achieve. So I want to mention here, of course, power to heat. So dumping excess renewable electricity into heat storage. Heat storage tends to be very cost-effective, definitely more cost-effective than anything like battery storage we discussed before. But it obviously means bringing together different players and especially on distribution level, meshing our network more or providing really taking a focus on energy services rather than an integrated vision on energy services rather than just providing electricity or just providing heat. Secondly, I want to mention here hydrogen, or in other words, the mixed linking the electricity system with the gas system. So it's true that you can obviously use excess electricity to produce hydrogen through electrolysis. This is often referred to as power to gas or wind gas, if it's used from excess wind power. Very importantly, though, that this technology will need a CO2 source. So that is really one of the critical elements here. It's where do we get that CO2 from? We have obviously, we could couple it to some thermal power generation units. Another alternative is, though, to couple it to anaerobic digestion for biogas production. If we use anaerobic digestion, you usually produce CO2. So coupling that to a process to electrolyze it, which needs CO2, would obviously again be a system example where you perfectly we perfectly reuse a waste product and use it for another process like electrolysis and create a more integrated energy system as introduced by David in the introduction. So just to wrap up, we really believe that storage is important and we should continue R&D efforts and even deployment and demonstration efforts in storage. But we should not forget that storage is not a game changer. We have other options in the energy systems that enable us to integrate large scale of variable renewables. Cedric Philibert alluded before at a recent publication from the IEA, in where we show that you can, and you show how to integrate best practice examples on how to integrate variable renewables. It's so important as well that storage is very system specific. So it will depend on the specific loads. The loads obviously, if you have more, let's say, a peak load profile, there might be more options for storage than if you have a relatively flat profile. It's also important to look at the flexibility of the thermal stack. If you have an unflexible thermal stack, thermal power plant fleet, then there's more options for storage. And finally, which applications are needed for the system. So it's very important to go to make an assessment of local conditions. A conclusions for that obviously is that in terms of what policymakers should support is that we really believe in an application-based technology support. So let's assume you're a country and you see that an application like load following is the most important one for your country. So we really believe that then you should specifically have an open innovation model where you support innovation for load following rather than specifically pushing one technology which might lead you to suboptimal results. Finally, market design and regulatory and regulatory framework are key for rewarding storage and flexibility generally adequately. So there's a lot of research that needs to be done in that field as well. Finally, demand-side response, and in particular thermal storage appear particularly cost competitive, more competitive than many of the more electric and or battery-based technologies. So we cannot stress that enough, and we should not forget about this. Maybe appearing more maybe more low-tech solution, but often also more promising. Finally, the limitations is obviously interconnectors and power system interconnections provides a lot of flexibility as well and could link different balancing areas. So this has not been in detail assessed here and needs further investigation. And finally, the uncertainty over the future load profiles. If you look at electric technologies such as electric vehicles, but also maybe heat pumps. So with that, I want to finish here and give the word back to Marcus.
Thanks, Steve, and thanks, Luis. Steve, you already mentioned for storage the importance of market design and also how these solutions will be financed, and that provides a nice segue to the next chapter here on attracting finance for low-carbon electricity generation. I think Cedric also alluded to the fact that many of these technologies are characterized by high upfront investment costs and very low running cost. And that in itself makes financing these a very different challenge than, say, a natural gas plant and so forth. So what policy advice can we glean from these technology analysis that we do? I think many of us are asking these questions. So please, I think it's Dave Elzinga who will actually present this chapter. So please, Dave, the floor is yours.
Great, thank you. Yeah, Manuel Barreto is the author of this chapter, and he's not able to be here today, so I'm just filling in. So when we look at finance, we wanted to take a look at it from the finance perspective and the investor perspective, and that it requires an appropriate risk return for the investor. And with many low-carbon technologies, the lack of a carbon price and the volatility that we've seen around that has really undermined investor confidence that in a way is going to be a long-term tool. So therefore, we really need to find creative ways to de-risk low-carbon investments to make sure that we can get the investment flowing if we really want to achieve the 2DS scenario. And risk allocation needs to be more important. So these are the highlights from this chapter. And let me be clear, we're not saying that a carbon price isn't important, but we do need to consider the fact that that hasn't been as successful in the short term as we had hoped. So what we see is that low-carbon technologies remain more expensive, especially in this transition period, but not only more expensive on the levelized cost of electricity, but also more capital intensive or capitally expensive. And so this introduces some challenges for investing. And what this does is it increases their exposure to market price. We see that right now wholesale electricity prices are largely managed by or influenced by the price of the fuels, whether that's natural gas or coal. But we see that with low capital costs and high fuel costs, this is logical for these technologies. But when you look at many low-carbon technologies, this doesn't fit. They don't fit the same model. So it changes both the economics and the risks for the given investments. And here what we do is we take a look at the risks that affect the different cash flows for an investment in a technology. And largely they can be summed up in four areas, that being regulatory risk, construction, market, and operations. And what you see is that how the risk influences the cash flow. Some, for instance, construction risk only happens during the building phase. But what you see is that the regulatory, the market, and the operations risk happen over the course of the entire project while its entire operating life. So therefore, again, low carbon technologies are different here than conventional technologies such as gas turbines or coal generation technology. So what we did is we tried to did some sensitivity analysis across a number of different technologies, looking at the main parameters were the electricity price, the load factor, the construction cost, and the construction duration. And we compared them on a net present value basis. So we looked at several technologies. In this case, on the screen, you have onshore wind. And what you see is that, for instance, the construction duration, there's quite a high level of certainty here for the construction. It's well known and well managed. Of course, costs can vary, and costs have the actual cost of the deployment has a huge impact on the net present value. But most important is the electricity price risk. And you see, as we looking at 1 gigawatts of capacity, as we vary it from about $50 per megawatt hour to 120, dramatically changes the net present value calculation. And we see, if we compare that now to nuclear, putting nuclear at the bottom, you see that the large capital investments that are required for nuclear power means that the electricity price risk is huge. But also, as we've seen in the development of nuclear power, that the duration of construction combined with the high upfront capital costs means that if you have an extension of 3 years in the construction of the plant, it has a huge impact on the net present value. So therefore, raising the risks for investment in this technology. So we really have two ways to look at this. One is improving the expected net present value. So increasing essentially the cost of capital, so that even though the risks appear and they're large and spread out, the return is high enough for investors to accept the risk. Or we can, in number two, try to make the risks lower and therefore decreasing the cost of capital and make it easier to invest in these technologies. And there are a number of schemes that can be used to do that. But what is interesting is that where the risks are held, whether it's the ratepayer or society in general that holds those risks, or the investors, depends on the different mechanisms. So if you just contrast a fully regulated market, the ratepayer incurs the entire risk. As you try the different mechanisms, you push more risk towards the investor. And the best way to manage risk, or I guess handle risk, is to make the risk fall to the stakeholder who can best manage it. So it's very important that the policy options, sometimes it is the government is the best one to manage that. Sometimes it's the construction company or the investor. So from that perspective, it's very important to do this transparently and shift it to those who can best manage it. Here we just have an overview of the different schemes, and I'm not going to go over this in detail, but what it does make clear is that different technologies really can use different types of mechanisms to support them, and it isn't a one-size-fits-all. So I'm going to close on this, and the key takeaways that I want to do, as I've briefly covered this chapter, is that financing low-carbon plants in a competitive framework really requires high returns on capital. So that's a bit of a danger, because if the costs come down but the cost of capital goes up, we lose many of those gains. A high carbon price could stimulate low carbon investment, but a sufficient price is quite unlikely, especially in the near and medium term in most regions. So therefore that means that in order to trigger low carbon investments, governments must consider different ways to supplement electricity markets. And lastly, governments need to make the risks more transparent to all stakeholders. We know that there are some risks in deploying new technologies. We do need to determine how we can best do that, but do it in a transparent way so that you have strong buy-in from society as well as the various energy system stakeholders. So thank you. I'll pass it back to you on that, Marcus.
Yeah, thanks, Dave. I think the financial innovation might be equally important to technical innovation that we've seen over the last years for deploying these technologies. So it's interesting to see the work of the IEA in this area. So moving on now to the last segment of the presentations, one of the new features of ETP now is a country focus. So each edition will have a focus on one country of particular interest. And now we'll hear from Keith Bernard, who's led the work on India and electricity generation in India. So please, Keith, the floor is yours.
Thank you, Marcus. As Marcus said, my name's Keith Bernard. I'm a senior analyst here at the IEA, and I drafted this chapter along with my colleague Luis Munuera. First, just a quick introduction on this. In this new ETP annual series of reports that we produce, we will feature a chapter on a partner country. This year we have focused on India. Next year it will be China, and in 2016 Mexico. So now with the chapter on India. Well, harnessing electricity's potential, which is the theme of this year's ETP, is particularly apt for India. India today faces unprecedented challenges few countries, in fact, have faced. 300 million, or around 300 million of its people lack access to electricity. Its per capita electricity consumption is less than 1/4 of the world's average, and the gap between supply and demand can be quite high at around 9%, and can be even higher during periods of peak demand. And over the next 20 years, India's population is expected to exceed that of China. Its demand for electricity is projected to increase quite substantially, and its power sector investment needs are expected to be among the world's largest. Well, India pursues a low-carbon growth strategy in its power sector, but it has to be mindful that it's linked quite strongly with its energy security needs and its energy access needs. So it's expanded quite significantly, or quite substantially, over recent years. Its renewable capacity through its solar mission, its new wind mission, and a host of renewable incentives that it applies. And it also has quite a significant program on energy efficiency. Its demand to 2050 increases markedly, whether in the 4DS, where it increases by a factor of 3, or the 2DS, where it increases almost as much, but by a factor of 2.5. An investment in low-carbon technology triples in the 2DS. Its CO2 intensity of power generation decreases due to as it follows a low carbon growth strategy in both the 4DS and the 2DS. To address its demand for electricity, India has been increasing its capacity addition targets over for many years now. From 1997 to 2012, that is in the 15 years from the start of its 9th five-year plan to the end of its 11th five-year plan, capacity increased from 86 gigawatts to 200 gigawatts, and in so doing achieving around 2/3 of its targets for construction. And it has been increasingly more successful in achieving its targets. Over the 5 years to 2012, that is during its 11th five-year plan, capacity increased more than over the preceding 10 years, with 75% of its construction target achieved. And 70% of the additions from 1997 were thermal, the vast majority fueled by coal. And coal dominates electricity generation in India's power sector. In 2011, 54% of India's capacity was coal-fired, and 68% of its electricity was generated from coal. And on the right, you can see the map of India. The purple shows the location of its main coal fields, and the red dots, the location of its major coal-fired generation plant. Over the next 2 decades, generation from coal is projected to fall to 56%. So the share falls to 56% in the 4DS and just 17% in the 2DS. With more than 1/4 of coal-fired generation in the 2DS coming from plant equipped with carbon capture and storage. India is particularly well endowed with coal reserves, but much of it is located in areas where it's geographically and technically difficult to extract. The location requires transportation over long distances to its electricity demand centers, and Indian coals have gradually, or over recent years, been reducing in coal quality and is now quite low in quality, very high in ash. As a result, its increasing demand and difficulty in access, plus the low quality of its coal, has led to a significant increase in coal imports. And here we see the targets for India over the 15 years to 2012. And you can see from the dots on the graph, that's the achievement. The blue shows the target. So achievement has been significantly below. Our target has been achievement has been significantly below target, but there are good reasons why these targets haven't been met. There are, for example, conflicts with land use. Much of India is forested or agricultural, and so good arguments are needed to turn that land over to power infrastructure. Statutory clearances are to a great extent barriers to further development of infrastructure, power infrastructure. Infrastructure in India is not well developed. For example, there is much investment required on expanding its rail for the transport of coal. Its grid infrastructure needs expansion to transmit and distribute electricity, the electricity generated. So increased capacity is not often or is often not effectively utilized. Generation capacity, for example, may not be connected to the grid, or the capacity of the grid may be too low to distribute or transmit the electricity during peak times. And grid losses are high for many reasons. And of course, operation of generation infrastructure often requires high volumes of water, and much of India is water stressed. Well, all future scenarios, whether it's a 4DS or the 2DS, require a heavy increase in power sector infrastructure investment. The weighted average cost of capital in India is currently around 15%. For coal, at a cost of capital above around 12%, investment in less efficient, less capital intensive subcritical plant is more cost effective. So we continue to see construction of subcritical coal plant in India. And while investment is not the only factor influencing infrastructure construction, it weighs heavily on the choice of technology. But I mentioned that India is more cost-effective to build subcritical plant at the moment. Well, from the 13th five-year plan, beginning in April 2017, it will introduce its policy preventing the structure of further subcritical plants, so that plants from April 2017 will be supercritical. And the cost of capital is also crucial for renewables. At a US-European cost of capital, renewables greatly increase in competitiveness. And in many areas, in many areas, wind at grid parity. India is abundantly endowed with potential for generation from wind, solar, geothermal and biomass, as well as hydropower. On this figure, you can see is from our ETP scenarios, where we see a great potential for cost-effective, low-carbon, renewable generation in India, particularly from solar, PV and CSP and wind. And as we saw earlier, India has been overachieving on its construction of renewable capacity. It needs to continue to overperform to meet the ambition shown in the ETP scenarios. And so with that, I'll hand back to Marcus. Thank you.
Thanks, Keith. So we now have about 8 minutes left. We'll have time for a few questions. Just to let you know that we've received a tremendous amount of questions, and those of you feel that we haven't answered your question, we will try and get back to you on an individual basis to reply and respond as best as we can. And of course, you're welcome also to explore our website. You see a screenshot here from one of the visualization tools that are there at the ia.org/ETP. So please go ahead and explore the data there. So let me then dive into, I think I'll pass 3 questions in the string here, and I'll let you answer them before we perhaps return. So first to Philibert, we received a question here highlighting the fact that in order to deploy solar, you need a fair amount of grid services that at least some people argue are not necessarily priced into the cost of solar. So basically, solar relies on services from the grid and backup from the grid that are currently sort of taken for granted, not priced properly. We see that in the United States, where some connections need to also pay a monthly charge, for example. So could you reflect a bit on that? Then to Sean and Simon on the gas chapter, we heard you saying that from somewhere around 2030, gas will need to gas will no longer be sort of a low carbon option, but rather emit more CO2 than we can handle on a per kilowatt basis. So what does that tell us around stranded assets, and for how long should we view gas as a viable option to reduce emissions? And is there a case to move out of gas sooner perhaps than people think? with that in mind. And finally, to Steve on storage, and Louise there, you say that it's not a game changer, but how important is storage compared to other flexibility options that we heard you mention? Could you perhaps just give us a for dummies answer on that fairly difficult and complex question? So Sadiq, please could you start?
All right. Thank you for the question about grid cost. I think it's somewhat more complex than you might think. First, if you look at utility scale plants, developers usually have to pay for the connection to the grid, and the prices to pay are very different in various countries, so you find a great variety of situations. But I think the question was possibly more about distributed PV, where indeed the grid parity definition as we use it means that the cost of PV is at or below the variable part, that is the per kilowatt hour part of the retail electricity prices. And those retail electricity prices include the cost of the grid, and usually, although these are mostly fixed costs, they are recovered through variable payments, through per kilowatt hour payments. The bulk of these costs is usually recovered through variable payments. But I mean, the first question is that fair? And one may just respond that why should PV pay for a grid that it does not use when it's doing self-consumption? And the response, of course, is slightly more complex, because indeed the owner of the plant, who is also a consumer, will change his or her profile of consumption in a way that may or may not reduce the cost it creates for the grid, depending on the match between the PV resource, PV generation, and the peak hours. Because most of the costs for grid are incurred with peak hours. So it all depends. In countries where you have a good match, where most of the electricity is consumed in summer afternoon because it's driven by air conditioners, then PV first reduces grid costs. And there is absolutely no reason why they would be charged or finger-pointed about grid cost recovery being damaged. In countries where the peak is in winter and after the sunset, of course the match with PV generation is not that good, and indeed you will have to recover the grid cost on a slightly lower amount of kilowatt hours. So this means you may have to progressively and cautiously reform the tariff structure. Some say we should increase the fixed payment and decrease the variable payments, but this would lead to provide incentives to consumption, and this is not what we want. So basically, it's more interesting to go into time of use pricing, into providing more direct incentive reflecting the true cost at each time of the day and day of the week and season during the year, to have a more reflecting cost structure. But these changes have to be made with caution, because they have a huge implication for all people on the grid, and not only for the PV prosumers, that is, those who are both consumers and producers. Thank you.
Great. Marcus, I guess I can pick up the second question. This is Sean here on the question around, I think, the timing of new build gas-fired power generation and the hot topic of stranded assets. So I guess I'd kind of give a concise, hopefully three-part answer. First is that whenever one looks at data from ETP or any other IEA publication that shows aggregated world results, one has to be pretty careful, because that hides a lot of really important regional trends. And Cedric had a good example of that, looking at the way that solar is deployed differently across different places with different levels of direct normal radiation. You know, the figures that I was showing for new build gas hide a lot, or aggregate for the globe and hide a lot of global trends. And if we take it apart and look more closely, what you do see is that even in the 2-degree scenario, you do end up with something like 500 gigawatts of global net increase in gas-fired generation in the 2-degree scenario through 2020. And in non-OECD countries, you see that increase still happening through roughly 2040. And you also see at that point, then you start to see, as I said, in that time period, 2025, 2030, depending where you are in the world, start seeing CCS coming in. So, those, and in our model, those aren't quote unquote stranded. None of those are stranded assets, quote unquote, because you know, you define a stranded asset as being something which cannot be operated the way it was envisioned at the time the investment was made. So it has a shorter life than was originally anticipated. That's basically one way we look at it here. And in the way the model works, it doesn't have stranded assets. It has perfect foresight. It's making these investments in an intelligent way. That's not how the real world works, of course. But so in our model, when we say yes, we see even an expansion in the near term on gas-fired power generation, that's actually generation that makes sense. None of that is stranded per se. So there is still a need to be building, even in the near term, unabated gas-fired generation in some regions of the world. I guess I can pass it on now to Steve.
Oh, Stephen. Yes, Stephen. Okay.
Hi, just to answer that question, yeah, so Steve speaking, just to answer that question on storage, and you know, that we said it's not a break, it's not a game changer, and especially compared to other flexibility means. And again, it's very important to say here that storage is per se a system technology. Storage needs electricity, is storing that, and is discharging it. So it needs to be integrated in a system, and there's other technologies, competing technologies that today, not just based on today's cost, but even in the cost that we expect in the next 10 to 20 years, look more attractive. Namely, still thermal generators. Yes, thermal generators are struggling today to make an investment to be profitable, but still on the cost basis, they are still more interesting than storage. So this just as an illustration how much a storage asset could struggle in the same situation. Then we have obviously demand-side management, also a very cost-competitive solution. We see it in markets like PJM, that since they allowed demand-side management to bid in capacity for capacity adequacy in their capacity adequacy market, it's been a huge increase, so huge success. And this is mainly assets that are being rewarded for providing a service that costs nothing extra, if you want to say, to the owner has this asset, is sitting on this flexibility, and is just offering it on the market. Finally, there's interconnections. I mean, there's a big drive to interconnect our markets to build really continental markets. I mean, we see that in Europe, we see that in the US, but we also see it in China, for example, where obviously the continent, the country itself has a gigantic size, but is being interconnected to all regions, and that alone can provide a lot of flexibility as well. So these things are, interconnection is often built for other reasons, but provides a lot of flexibility. So, as a conclusion, you know, and to add to that is thermal storage. I mean, if we integrate the power system with thermal networks, but also with just thermal assets providing heat storage, you can provide a lot of flexibility, which is all more cost competitive than storage to what we see today or in the longer future. I'm going to give it to Luis, who wants to add a few wider perspectives on that.
Okay, so just to add on that, I think something important to realize that providing flexibility is often a very different business model from selling bulk power in wholesale markets. So there is some immediate potential, for example, to retrofit pump storage plants to provide more firm capacity. Most of them, they're basically designed to sell large amounts of power during peak periods to leverage arbitrage opportunities. But to provide firming capacity, you need other components, for example, variable speed pumps and so on. So there's some potential for these plants to immediately provide provide greater flexibility. And now, the second point I think is important to make is that I think this has been said also before. When we're talking about system integration technologies, the word system is the operative term. It really depends on the system. This is the reason why we decided to focus not on trying to provide a global perspective on storage, which we did, but also to try to look into 4 specific regions. We looked at the US, we looked at China, we looked at India, and we looked at Europe that cover, according to our projections, around 75% of the total final electricity demand in 2050. And there we saw very different trends by region, depending on, for example, how the system load curves, the electricity demand curves would evolve with development and the changing structure of the different economies. And also, as new energy services are coming in, we see a lot of heat pumps coming in, a lot of cooling, especially in Southeast Asia. And when you factor these new services in electric vehicles, you also have to factor in what potential for flexibility can be provided from these resources and also from existing resources. So again, the existing system, the potential for the growth for different energy services, the flexibility of the thermal stack, all that contributes to what is the local or regional potential for or attractiveness of storage technologies.
Okay, thanks, Luis. And so we're already a little bit late, but let's go on for another 5 or 10 minutes maximum, so we can all come home in time to watch Mexico, Cameroon for those who root for those teams. Just 2 questions then to Tali on transport. I think are particularly interesting. You know, one of the most common ones on especially passenger EVs is this chicken and egg problem. Should governments try and support infrastructure like charging stations to stimulate the uptake of electric vehicles, or should they rather incentivize people to buy the vehicles and trust the market to supply the infrastructure? Another question, I guess a little bit outside the scope of this, but which is super interesting, is to what extent the IEA are looking at penetration of natural gas in transport. I know that you have work in the pipelines. Maybe you could mention just a little bit on that. And then a final sort of broad question, I guess, for you, Dave. Now we've heard all these, seen these presentations on technology options that exist to dramatically reduce the emissions of CO2 from energy-related activities, but we haven't heard so much about what the investment needs really are to realize these scenarios. So I'd like to just ask this sort of simple but critical question: is this really feasible from a cost perspective? How much will we have to pay to realize this 2-degree scenario, or scenarios maybe?
Okay, thanks so much, Marcus. This is Tali. I'll take the first the transport questions and then turn it over to Dave. So regarding the first question, the classic chicken and egg, it's a really interesting question. If we're looking at different modes, obviously there are different, let's say, roles the national governments and cities and private sector will play if we're talking about rail electrification versus two-wheelers, buses, trucks. You can imagine for electrified trucks on highways, you certainly would need, you would arguably need a stronger government public role to sort of work as a public-private partnership to launch such a thing, whereas two-wheelers are a little easier to do in that sense. So what role should there be? I think what we're seeing is that national governments are taking more of a role in promoting incentives, and so developing and helping spur the market for passenger EVs. As for the infrastructure, we're seeing a lot of cities are taking roles and coming up with innovative solutions. I guess in some sense, you know, it depends a little bit on what you're looking to do. So if one of your goals is to say improve air pollution, reduce air pollution in a city, then as a city you can say, okay, well, we're going to incentivize that by only restricting some parking to low emission vehicles. So that's not a direct financial subsidy per se, but you're trying to achieve one or several goals by doing that in that sense. So non-financial incentives are really quite important and seem to help spur both market uptake of EVs as well as infrastructure. On the question on natural gas, it's a good timing because our colleagues in GCP, or our colleagues, came out with a medium-term gas market report just this week. So I urge everyone to go to our website and have a look at some of those results. I wish I knew them all by hand, but I don't. What I can say from the transport point of view is that we're seeing a lot of natural gas and even LPG. There are such vehicles around the world. LNG for shipping is a whole different animal. But China is now growing both CNG and LNG vehicles. So that's, I guess that's a bit on the present situation. Though you could argue that natural gas vehicles and LPG vehicles have been around for a while, and they face many of the same hurdles, which really boil down a large part to infrastructure issues, which is something the government needs to look at. So I'll turn it over to David.
Okay, thanks, and thanks to all the authors, and it's Marcus. Thanks for giving me the last word. I think on this question. I think this investment question is very important. When we look at the energy system in general, we see a significant need for investment. Even looking at our business as usual or current trend scenario, out to 2050, we see that the overall energy system requires an investment of nearly $120 trillion. If we look at, instead of going at current trends, we move towards a sustainable energy system, towards the 2DS, we see the investment is just over $160 trillion. So it's about 44 trillion more to develop a system, a sustainable energy system that aligns with the 2-degree scenario. So 44 trillion, that's still a lot of a large additional amount. But actually, when we look at the fuel savings that come as a result of this, we see that the $44 trillion is more than offset by the 115 million in fuel savings that are accomplished in the 2-degree scenario. And so that's undiscounted. But even if we apply a very high discount rate of 10%, we see that this still pays off. So from that perspective, it does make sense to invest in the 2-degree scenario. But it is a different investment regime, like we've talked about, of higher capital cost, a shift away from the way we're doing things now, a shift from where we're investing now. And this really takes a long-term plan and significant leadership from both governments and private sector.
Well, thanks, Dave. That's certainly encouraging these times of pessimism sometimes around it possibly even reaching the 2DS. So with that, I would like to thank, of course, the IEA for producing this report. Congratulations of yet another great publication. And even more, all the attendees of this seminar. It's been very interesting to see all the questions come in. And again, we will try and get back to you offline if you haven't had your question answered. And please do also explore the IEA website, iea.org/ETP, for lots more. As Jean-François mentioned at the beginning, ETP is more than a book. It's a series of publications and also a tremendous online resource you can download and view a lot of the data that's in the book and even more beyond that. So thanks a lot. Have a nice weekend, and hopefully we'll meet again soon, either online or in person.